Welcome to last option. This is a solution video of previous question that we had sent from this channel only. So these were the data that were given to us for question number 1, and figure somewhat like this was shown to us, and we were required to find that how many times I need to rotate this so that I can get first electron knockout of this metal surface. As we are considering the wave nature of light, means particle nature of light has been ignored here. So wave nature is considered. So in wave nature we transfer energy continuously. Rather in particle nature we transfer it at an instant in the form of photons. So I have to keep on adding energy to this electron until its energy becomes work function of the metal. Then only it can get out of the metal surface and I can detect, so that I can stop this rotating this polarizer. So I can write here that until the energy of electron becomes the work function of the metal, I have to keep on rotating this polarizer. And how to find this energy? As we have told that it's a wave nature, so we can consider intensity of light. That means how much intensity is going to fall onto this metal. But one more problem is here, that this intensity is not constant to this metal. So I need to integrate that energy. I can add those much of energy in non-integral form only, so that I can get total amount of intensity that is going to fall onto this metal. So for an instant we can tell that energy is equal to intensity. Intensity means how much energy is going to transfer to metal per unit area, per unit time. So considering small section, you can get here. So this would be getting intensity I for an instant. So this is getting per unit area per unit time, so I need to multiply it by per unit area, and for how many times I have been transferring this light. Okay, so this is the first thing about it, and I will keep this as metal function, work function of a metal. But this I is not constant, so here I have to do integration. So integration is also need to be performed. With respect to what? With respect to this small time, I would keep on adding this energy until its energy becomes work function. So I have to do something with this one, because these area of the metal are constant and time that is that we will get would be constant. So let's see that what we have to do with this intensity, which is playing an important role in this case. So in order to calculate that how much total energy is going to transfer to this one, I have to do something with intensity. So if I can find that how much intensity I have transferred to metal during the whole rotation, so I net can be integrated by what is the amount of intensity that is going to rotate for an instant. So this is I into cos square of omega t into d omega. So this you can get from Malus law. Okay, so I need to integrate it from where to where? Let's stop once. Again, let's move one step again. So in order to get total amount of rotation, this is the amount of energy that I am going to get per unit rotation. So I have to multiply it n times. Means how many times I have rotated that polarizer, I have to multiply it to it. So n times, let the number of rotation of the polarizer be n. So integrating I into cos of this omega t is nothing but theta, that the angle which this polarizer make with the plane. So let's write it theta into d theta, and this theta for per unit rotation is going to change from 0 to 2 pi. So with this I am going to get that how much total amount of intensity, that is energy per unit area per unit time, is going to fall onto this metal. So this would simply turn out to be n pi I. So this is the amount of intensity that metal will get. So let's put this equation in the value that we have simplified from here in order to get the final equation. And there is important thing. that is time, that how much time would it would have take, I can relate it with this omega. So let's see this. So now this I is equal to I n pi, area is A, and this time, this is the time that how many total time would have been elapsed since I would have turned it on and get the first electron out of the metal surface. So if I can calculate what is the time required per unit rotation and multiply it by number of rotation that I have done, I can get it so easily. So number of rotation is n into time taken for per unit rotation is nothing but 2 pi by omega. Hope you got that hint. Okay, this 2 pi by omega is work function. So now all the ambiguities have been resolved. I n pi a and 2 pi by omega is metal work function. Now what I have to get? N. So simply n can be found from there. So this n equal to 5 times omega upon this 2 pi square into area into I. This would be n square, 5 omega 2 pi a n. Okay, this was n square, I can make it root. So this would be the answer for how many times I would have to rotate it completely. Note this word completely, it's important. So this is the answer for first one. Let's see the answer of second one. It's more interesting because very less information was given about question number 2. So user was having a free mind in order to solve that question. So let's see. So for next question, it was given n power dx upon dx and you were asked to integrate. But notice one thing, you have not been given that with respect to what you have to integrate. So you are having free choice that whatever you may take, no one is going to stop you. What you may do is, one more information is given that n belongs to R. First approach, case 1 we may do, that we are going to integrate this with respect to dx, because you might be seeing dx and you keep on doing integration with respect to dx. So by nature you might perceive this as integration with respect to dx. So you would have multiplied dx, let's see, okay, n to the power of dx upon dx square into dx. Now dx is approaching to 0. I have made the formality that I have to do while doing integration, that is some part should be there with a small value, dx, dt, d alpha, whatever you may take. Here dx, and this is some value that you have to manipulate. So what you may do is apply the limit. So here limit of when something approaches to 0, still you are having one more option, n to the power of dx upon dx. First thing you may do is when dx approaches to 0, so that means small element along x-axis is approaching to 0. So something power 0 upon 0 where n is positive number, what you may do? Here arises more number of cases again where n is greater than 1 or n is belonging to 0 to 1. Two cases arise. See, for n greater than 1, let's do 2 power dx upon dx. 2 power 0, 1, 1 by 0, limit does not exist for this one, where it's somewhat near to 0 and 1. In between 0.5 power dx, 0.5 power 0, 1, 1 by 0, again not existing. So one more case here, you have to specify this when n is somewhat equal to 0, that is n is tending to 0 but not equal to 0. So one more thing you have to apply here, that it's again approaching to 0. So 0 to the power 0 upon 0, it's not equal to but approaching. So this whole value would again approaching to 0. So this 0 upon 0 form is here. Now you can proceed. What you may get? Apply l'Hospital rule. That's option with you. Now here this dx, this, so double limit you have to apply. So you can take first this one, next this one. So you will get n power dx into ln n upon 1. Where it's approaching to 0, and this value is approaching to minus infinity. So again it may arise. So this was just a hint for you in order to solve this question. This is quite special, you would say, because number of cases are keep on increasing when you keep on talking like this one. Then again you can do with respect to dn. This dx is somewhat not related to integration. You can assume that because I have not mentioned anything. So by dx these things are arising. Again it will make some changes here, and there is no possibility of it in this case. So keep on doing this, and let's talk more about this in the next video, because that's a more interesting form of question you are getting. So let's keep this for this next one. I know the answer. Okay. So let's take this third question. It's this was given and you need to find dy by dx at 0, 0. So what you are asked to find is dy by dx at 0, 0. So by directly doing differentiation you will get to this result. So by directly doing this you will get this as dy by dx, and you need to find its value at 0, 0. So means again here you have to apply limit, buddy, because you are having x, y again and it's tending to 0 simultaneously. So this whole value I have to check. So limit of an x, y both approaches to 0, at that point I have to find. So minus of a square x plus xy square upon x square y minus a square y, limit at this tending. With the easier approach, what you can do, you can replace this y with x, so that this double limit can change to single one, and that's quite easier one in order to get to this equation. So by doing that you can proceed one. I can directly tell you the answer of this. This is somewhat equal to 1. So just find value of this from this equation in terms of x and a, put that value here and apply simple limit. Then you will get something like 0 by 0 form. Again you can do l'Hospital, or by one step you can get it easily equal to 1. So this is the solution of third one. So nothing like special to this question, but this double limit might change you. So consider this fourth question. It was from differentiation. Yes. So you are given like dy by dx plus y e power t into d alpha upon dt equal to 1, where alpha and t are independent of x and y. So while doing this integration you need not to worry about this term. Yeah, it will be treated like a constant. But in question you are asked to find the final result. So after that we may face. So first solve this one without considering much about it. So it's like a form of this, that is integrating factor directly you can go it e to the power of integration of px जो y के सामने है, that means front of y. So let's consider first this as constant, something equal to k. So k into dx, that you will get. Therefore e power of k dx, this you will get. So this is the integrating factor with which after that applying you can get this easily one. So e power of kx, now y into e power of kx equal to integration of 1 into e power of kx into dx plus c was given, but as it is satisfying 0 comma 0, ultimately you will get as nothing like that. Okay, y power e power kx equal to integration of this, that is k e to the power of kx plus c. So this k is known to you, you have to find this c. As it is crossing 0 comma 0, put 0 here. So this whole will turn to 0, but this won't. So here c equal to minus of k, not this one. So y e power of kx equal to k taking common from here, that is equal to e power of kx minus 1. Now here k again is a function of d alpha dt, where nothing has been told about e d alpha on dt, that means alpha and t, so they might be related. So after solving this, you would be able to get that relation, so which can further be changes to this one, and simplified version would be this one. So you can end up here, because everyone is having mathematical limit, or you may cross this limit and reach to the final answer. It won't be challenging, but it would be an exciting journey. If you wanted to take that, you may take that. Don't forget, I know the answer. So this is question number 5. The main concept behind this is the angular momentum conservation. As there is no external force, their motion is only due to their mutual interaction, we can apply total energy conservation or angular momentum conservation about their center of mass. So let's write L initial, that is what the angular momentum at initial time, that is equal to 2 times of m v naught r. V naught is the velocity at that time, m is the mass at that instant, r is the distance from their center of mass. So this can simply be m naught times of 1 minus of v naught square upon c square into v naught into r. Why is this so? M is the rest mass. That means if it would be at rest with respect to an observer, then its mass would be m naught, and as it is moving with the speed of v naught, its new mass would be this much, and other factors are like that only. And for L final means the instant at which we are observing, that means when they are a distance r apart. Again you can write it as m times of v dash r, or m dash would be there, or m prime would be there. M prime is more fantasy like, but whatever you may use, by just specifying that what it means. So this also would be 2 times of this one, that's why I have cancelled that and directly written it in form. So this can be m naught times of root over 1 minus of v1 square upon c square into v1r. So by just equating these two, you will get the answer. So let's this job to be done by you. So directly you will get v1 as 2 times of v naught upon root over 1 minus of 3v dash square upon c square. So this would be the velocity. So directly you can observe that it's increasing, but one limitation is here, this v dash must not be somewhat near to speed of light, because otherwise this factor would change a lot. So this is comparable to speed of light, but not exactly or not exactly nearer to the speed of light, but somewhat comparable to it. So this is all about 5 questions of this, and let's take this challenging question in the next video. I will just post it in the next day, so that you can get that challenge question, and that would be quite interesting. So whatever concept you have learned in class 12th or engineering mathematics, that can be applied, and with that you will get the answer. So thank you for this video. जय हिंद जो होता है।